And this theory relies in the mesoscopic nature of all the processes I have been working, and specifically the formalism I have been using is the mesoscopic non-equilibrium thermodynamics, MENET, of active systems. And I will try today to go from chemical reactions to perhaps tissues if we have enough time. And the talk is going to be divided in, hopefully, in 3 parts, but the main one is the first, because I want to present all the fundamentals of this formalism. And I will do it through a chemical or an enzymatic reaction. And the second part is I'm aiming to present the equations to describe the collective dynamics of active particles or active nematics or even cells. And finally, if we have time, I will present briefly a bit more about the effective potentials as a criteria to understand the emergence of a structure and function of self-organized structures, to understand the formation of structures and its function, such for instance, in tissues. So I would like to start with some processes that we can simply describe as A going to B. That could be a chemical process that, for instance, describes I have a molecule and then this got broken, and we will have 2. This is the first state and this is the second state, and we can more or less, we will have some intermediate states, and this process can be characterized by, for instance, the length of the bond. So for instance, if we plot here the energy of this system, of this reaction as a function of the length of the bond, we can have something like this, for instance. If we have an enzymatic reaction, this energetic profile is going to change a bit. We will have intermediate states. It could be even more complicated as a function of the length of the bond. But we have several more processes like this one, as for instance, the phase change, where we have a small, thank you very much, some liquid molecules going to the solid state. Then we have intermediate states, and we can parameterize this process as depending on the density of this and this state. And if we also, again, describe what is the energy along this characteristic coordinate, it would look something like this, for instance. And I can mention even more processes like the polymerization process. Sorry, this is phi. This, sorry, no, it's going to be again phi. It's the energy or the energetic barrier to describe this process. So they are going to have the same energy, but they have the intermediate state is the unstable state. So this can be, sorry, this is not L, this is the density. We can do something similar for the polymerization process. The self-assembly, also the assembly of microtubules in a sequential way, could be also described like this. The passage of a particle along a channel that is known, yeah, it has rugosities. It's not the cross-sectional area is not constant. It also could be described like, for instance, if this is a position x, and I plot the energy as a function of x, we can have something like this too. So, and so on. The point is that if we are able to, this kind of process, to characterize with a coordinate, a variable, and we can associate to the process an energy barrier, we can describe it using this formalism. So kind of the most difficult part is to be able to characterize each process with this coordinate. For instance, for chemical reactions, this proposal I think it was done more than 60 years ago to understand these energy landscapes, to understand the chemical reactions, enzymatic reactions. But it could be done the same for these other cases. Also for the growth of a crystal as a function of the radius or the surface area, and so on. There are many examples that can be characterized just by one variable. There are more complicated processes, as for instance, A going to B, but A also can go to C. Then we are not going to have only one dimension, but two, and so on. It can be generalized. Anyway, and these processes classically have been studied by Kramer's problem, the first stage passage, if I'm not wrong. We can also use master equations. We can use Fokker-Planck equations as well. The Smoluchowski versions for these agglomerations, for instance, or for the polymerization. If we also consider these processes as purely stochastics, we can go to Langevin. So this classically in non-equilibrium statistical physics is what was applied for this kind of systems. Of course, not necessarily from this perspective I'm introducing for you today. But then what I want, or my aim is to present the formalism, how to apply the mesoscopic non-equilibrium thermodynamics formalism to understand this kind of processes. Is the core, is the theoretical core, is the tool, is the main tool to be able to describe up to active matter systems and also tissues. But let me focus on these very, very simple cases in order to present the fundamentals. So if I have a system where A is going to be, if there is only one reaction there, we cannot do statistics at all. But if we have several of these replicas, we can do some statistics. As well, we can have a big system where several of these reactions are taking place simultaneously. Let's assume that in this system, in this case, is a closed system, and let's assume that they are not going to be gradients on the space. So let's keep it very, very, very simple. So we can characterize, as I mentioned, the process with the length of the bond, but we can also say, okay, let's say that the state here this corresponds to the state A, and here to the state B. And this is a coordinate gamma, or the reaction coordinate, process coordinate, internal coordinate, as we want to call it. And for A, it corresponds to alpha equal to 0, and to B, alpha equal to 1. Let's agree on that. And we can then say, what is the probability to find my system and a state alpha at the time t? So, and this is the we then define this as the probability density. Okay, B is this whole state. A is this whole state. Is this molecule? Yeah, this is the let's. Yeah, exactly. And I can illustrate that much better. I will, let me.
Continue.
Yes. If we go, this is a group, let's say, and we have here the bond. It has a given length.
Yes.
Then it start to in this perspective, to be the bond start to be how to say, it's going to be longer. Yes, in the distance, the main distance, the average distance between this atom and this other one, and the transition from here to here could be something more or less continuum. Is not continuum at all. The continuity, yes, we can discuss that, because when it's very fundamental reactions, it is not necessarily at that continuum. I agree, and this is a limitation. There is another problem, for instance, if we have the protein folding, and we have two functional groups, it is going to be, these groups are going to be closer and closer and closer till they reach the final state. And this transition is more or less continuum, it's more or less. And this is our assumption. And the point is that we are saying that each possible intermediate structure each possible intermediate structure could be, we can relate one of these points in this energetic barrier. So we can construct these energy landscapes. It is even clearer when we go to this protein folding stuff and the other and enzymatic reactions. For these very, very basic chemical reactions, yeah, I agree. It's not completely clear in that way, but it's more or less continuum, and we can more or less apply this mathematics. So if I may continue, here we can evoke the conservation of the probability for the system. If there is not flows to the system, we can write it like the variation of the probability current as a function of alpha, that is our independent variable. At the same time, we will write the Gibbs entropy change in the system. That is the 1 minus 1 over T, the integral of the chemical potential of the system, of the component, sorry, times the change in the probability, all integrated in alpha. If you don't like at all this continuum approach, we can also write it as discrete. But let's take this very, very easy example to go on with the formalism, if you allow me. From this Gibbs variation, the Gibbs entropy variation, if we take that the process takes place along a differential and in a delta t, we will see here that we will have approximately the entropy change, or the entropy rate in the system. Since the system is closed, here what we are having is the irreversible change of the entropy, which is called the entropy rate.
So you just told us you have a system in which there are many A's going to B. Mm-hmm. So each of them has an independent reaction coordinate, no?
Yes.
So is your entropy the sum of those? What do you your alpha should be like an n-dimensional vector, right?
But you mean all we have several reactions A going to B, or you were referring other reactions A?
You said you have a system of many reactions A to B.
Yeah.
And each of those has an alpha, and each could be at different points along alpha.
Yeah,
right?
each.
So this sounds like it's describing one specific A-B reaction.
No, this is the reason. This is the probability density of finding my system at state alpha, because if you go just for one, No, indeed, sorry. This is the reason we talk about probabilities, because we will have several of these reactions of A going to B. Each of them could be could be in different values of alpha, but statistically we can define this probability density. What I will then show at the end, maybe I should write here what I want to obtain is that I can get Langevin equations, and then you will have a bunch of reactions describing each possible reaction. So you have a set. And from this Langevin, you can obtain a master equation or Fokker-Planck equation. So I'm going to obtain Fokker-Planck equation here from this perspective. So yeah, each reaction could be in a different alpha, but this is the reason we are talking on probability densities. Okay, this variation of the probability density as a function of time, it's what we have here in the conservation of the probability, that it holds for, it doesn't matter if we are close or far from equilibrium, it always holds. And from here, the important is that when we replace this one here, we are going to obtain, after integration by parts, we are going to obtain the probability current times the thermodynamic force. For this, I have to assume, or I have used, that the currents in the boundaries, so in alpha equal to 0 and 1 is equal to 0, and it is because there is not other state given main A, and B is not going to transfer in another state. So there is nothing going to C, or there is no D going to A. So this is the reason it's closed in this space. This is the space of the reaction alpha. Okay, now we evoke Onsager formalism. He cleverly proposed that these currents are proportional or depend to a coefficient times the force, thermodynamic force, that is here in the entropy production. And something that we are considering is that this is not necessarily a constant, that can also depend on the probability density. And that will allow us to explain chemical reactions that are not driven just for the difference of the chemical potentials as in classical irreversible thermodynamics was proposed, but depending on the fugacities.
Yes, I have a question just to try to put all the pieces together. How is this formalism related to just describing the concentration of molecules in a state B with a master equation and some reaction rate?
How, can you repeat me, please?
So usually the way I would describe this problem is writing a master equation for the concentration or the number of particles in a state B.
Yes.
And just try to obtain some probability distribution function. Yes. How is all that formalism related to here, where you introduce this alpha coordinate, you have entropy production, and you have chemical potentials that are not appearing in the other formulation? So how is...
No, that's a very good question. Because what I'm writing, what I'm presenting in this formalism, it's we are going to obtain Fokker-Planck equations from entropy production. So it's we are going to obtain dynamic equations, evolution equations that are thermodynamically consistent. So that's the reason, because when we propose the master equations to obtain the concentrations, the important is perhaps to define the rates for some matrix of forward and backward flows, currents. But then I'm building everything from entropy production and conservation of the probability. So all these approaches are going to be the same. Indeed, with what I'm going to obtain is all these classical non-equilibrium ways to understand the system, the non-equilibrium processes. So this is a thermodynamic formalism to obtain what has been done. And the idea is because we are assuring that thermodynamically is going to be consistent, which means that entropy production is well defined and it's positive. That's key. It's positive because there are some models in which that you can propose, but then when you compute entropy production could be negative, and then there is an inconsistency. So that's the reason I'm taking the time to build to obtain a Fokker-Planck equations from this. Okay, the chemical potential, we define it as it has an entropic part that is kBt logarithm of the probability density, plus the energetic part that is this potential barrier, which each means that the reference of the process of the system is this energetic profile or energy landscapes that can be built a priori from previous knowledge from equilibrium systems. When we insert the chemical potential here in the current, and we then insert that in the conservation of the probability, we are going to obtain the Fokker-Planck-like equation. So if I will go a bit faster, this L, we can define it as the diffusivity along the alpha coordinate over KB. The units are going to be consistent. So we have the alpha, and we have here the second derivative of the density probability as a function of alpha, plus this diffusivity over KBT, probability density, and then the derivative of this potential phi. Oh, sorry, I forgot a derivative here, respect to alpha. Okay. So this is the Fokker-Planck-like equation that I wanted to obtain from all these steps. It's like 6 steps. Conservative of the probability, defining Gibbs entropy, obtaining entropy production, defining the probability current, writing the chemical potential, and then we obtain Fokker-Planck. From Fokker-Planck, well, this is the diffusive term that is also related to the noise, white noise in alpha, and this is the drift term, or also the driving that gives the driven force, where, from here, if we can fulfill 2 or 3 conditions, we can obtain like Langevin equations. We can use Ito's formalism, Stratonovich, but for instance, we can just write how is evolving the independent variable that is going to depend in a noise, in a white noise. And here the driving term is related to this part that is the derivative of this potential. Everything in alpha. Yes, in alpha. So this is a way, this is a kind of, yes.
Sorry, do I see correctly? You have a multiplicative noise here? Alpha, it's alpha times the noise?
Alpha times the noise.
Alpha, am I reading that correctly? 2D alpha square root times the noise?
Yeah, it's the square of 2D, yes, this is the diffusivity in alpha.
Oh, the diffusivity, it's sub alpha.
Yeah.
It's not times alpha. Okay.
No, it's not, no, it's in alpha, Yeah. Yeah, I'm sorry if it was very big, yeah. Yeah, it's the diffusivity along this coordinate over this potential barrier. This is the interpretation in this case. From here, in this point, we can also, if we solve this, we can compute the entropy production. And from this definition with Onsager, the entropy production is defined strictly positive because the current depends on the thermodynamic force, and it's going to be, there is no way that is not positive. KB, and here the density, and then this one to the square, that is always equal, larger than 0. Okay. If I'm not forgetting anything else, we can also go to the quasi-steady state approach to be able to define the average rate that is going to be equal to a coefficient, okay, times the difference on the chemical potential in the state 0 minus, this is over KB, T, and the chemical potential in 1 over KB, T. When the chemical potential difference is very small, we will obtain what classically was proposed, that it depends just in the difference of the chemical potentials. And from here, we can also study the law of mass action. Yes?
Very stupid question from my side. The noise is always additive? Like when you write this Langevin equation in alpha, in this formalism, the noise is always additive. You cannot have multiplicative noise.
You cannot have different sources?
Multiplicative noise, like the amplitude of the noise depending on your...
No, yeah, it's just this one. It's just this white noise, not multiplicative noises. We can add to the noises, for instance, when we consider fluctuations in the hydrodynamic field or concentrations fields. Then yes, but this is perhaps the second.
So I think that's, sorry, Jared. Yeah, just to finish, because that's the way I'm thinking about the noise here. So what is the source of noise here in this alpha coordinate? It's thermal fluctuations?
This is mainly for the thermal fluctuations,
okay.
Yes.
Okay.
Yes.
Maybe I missed something, but why is your sigma related to the square of the gradient of mu and not the second derivative of mu with respect to alpha?
Here.
dp dt is dj d alpha and dj is d mu d alpha, so I see two derivatives of alpha, no?
Let me see if I... Yeah, it's because here, this is the minus dg d alpha.
Yeah, exactly.
And we integrate by parts.
Okay.
So you see it, or should I proceed? So we are going to have is mu times this.
I see. Yeah, I see now.
Yeah, sorry.
So you would have had mu, second derivative of mu with alpha, and you turned it into, I see. Thank you.
Yeah, you're welcome. Thank you for the question. Yeah, I went faster there, very fast. So I think I'm here. I have introduced this formalism that is key to obtain the Fokker-Planck equations or Langevin equations with thermodynamic consistency. Then, do you have any further questions before going to the second part? Yes, please.
So, I mean, I know there's a lot of criticisms of the reaction coordinate formalism, right? That many actual transitions have quite broad saddles, right? That aren't well captured by a single trajectory through configuration space. So if you, for instance, have a reaction where the breadth of possible trajectories is quite wide, where does this start to fall apart?
Yeah. No. It's a very good, it's a very, very interesting question. Yes, this is a very, very, very simple approach. For instance, when we deal with enzymatic reactions, for instance, the energy landscapes are by far more complicated, and at least you have to coordinates. You have also to consider the not only, for instance, the length of the bond, but also the configuration of the enzyme. So at least you will have two of these these process coordinates. Usually, this works very well for these processes, the A going to B. As I was mentioning at the beginning, we can also have A going to B, A going to C, and then this can go something crazy like this. And then the formalism, what we usually do is that here we define an alpha 0. For these other ones, we will have alpha 1, and for the ones that comes from here is alpha 2, and so on. So
I think you might have misunderstood my question. So, I mean, if you think of just a process A to B,
yeah.
but the A to B process is something like, I don't know, 2 configurations of a protein.
Yes, yeah.
In principle, you have 3 n coordinates, where
yes,
n
yes.
is the number of atoms in the protein, right? But
yeah.
then you distill it to 1 coordinate by
yeah.
some amount of choice,
yeah.
which is an approximation, because in
yeah.
reality, even if you follow, on average, a certain pathway, there is a breadth of fluctuations around that pathway, right? Which make it less energy than a free energy for the reaction path. I know that this can damage the results of this kind of approach. So I'm wondering, like, where would you change this approach to account for this, you know, the fact that the reaction coordinate is this projection to a very small subspace?
Yeah, no, I agree. This is one of the limitations, because to build this profile is kind of an effective profile if we have more than one possible path to go from A to B. So yeah, this is a limitation. Of course, if we want to try to understand this better, we add other coordinate, or as many coordinates as we can, in order to capture better the energy landscape that the process A to B can take. So I will say we can add more independent variables. But the idea of this thermodynamic approach is to decrease the number of independent variables that we need to use to describe the system. It's like, instead of doing how to say that, yeah, a Newtonian approach, we'd rather go to a Lagrangian approach, try not to use, or yeah, more energetic. But I agree with your point. The only way I can do better is to consider more independent variables to try to approach better the effective potential to the real potential that describes all these possibilities. And yes, this is a limitation, of course, on this kind of processes. Absolutely. Absolutely.
May I ask a question?
Yes, please.
Can you hear me?
Yes, I can hear you.
Maybe it's another way of asking the same question, earlier question. So you start with the essentially hypersurface in a 3n dimensional space, right? Because your system has many degrees of freedom. And what does it take to go from that picture, from my multidimensional picture, to the profiles that you sketched on the blackboard along a single coordinate?
So you
what do you require from all these other 3n minus 1 coordinates that you could essentially eliminate them and just keep alpha as your single coordinate?
Okay. One first approach to be able to do this is that the kind of the main variable, or the faster. This is kind of the limiting coordinate of the process, or the slowest process, the slowest trajectory that a process can follow, is the one that is described by this potential. If the other possible trajectories has more or less same energies or the same characteristic times, then this reduction to one coordinate will fall, as our colleague already also said. So yes, in this thermodynamic description, we need to eliminate these variables just by saying, okay, this is the slowest variable, the one that is limiting the process, and let's do this approach. For instance, in enzymatic kinetics, we have absorption, desorption, but also the reaction step, and we, for instance, focus on. Sometimes the limiting case is the absorption. Sometimes, depending on the enzyme, of course, it's going to be the reaction step. So, yeah, the key factor is, okay, what is the limiting step, the limiting trajectory that can follow the process. That's the reason we can eliminate the other ones. Otherwise, we need more variables.
Thank you.
You're welcome. Any other question? Okay. The second part, I will try to present quickly how I can obtain the dynamics of active particles to describe the collective motion, the interaction not only among themselves, but also the interaction with the medium, because then they also affect, because the particles are reacting, consuming the fuel. The concentration field is not constant, and some gradients are going to be created. As also, since they are moving, they are perturbing the fluid, so the hydrodynamic equations are going to have an extra term that a big part of the community in these active particles of active pneumatics call it the active tensor. Can also be seen as a source of momentum. And yeah, let's see if I will have enough time to go there. But I hope that with this description, with this formalism that is like a recipe, we first propose the continuum, the conservation of the probability. Then we have the entropy. From the entropy, we obtain the entropy production rate. Then the currents, probability currents. We also define here the chemical potentials. And if we go, once we have the currents, we go to the conservation of the probability, we are going to have the Fokker-Planck-like equations. And from there, we can not only obtain also Langevin, we can do coarse graining to obtain macroscopic equations, for instance, for the concentration of the fuel, and in some cases, also the hydrodynamic equations of the system. So if we have a system composed of active particles or active pneumatics, let's work with the catalytic Janus particles, in which a reaction takes place, A going to B. The particle has a position, X, with a given orientation, N. This chemical reaction also takes place at a given position that is in the surface of the particle. Is described also by a reaction coordinate alpha. The fluid molecules, we have fluid molecules. They have a velocity and a position. So we have three components, that is particles, that I'm going to use the probability density G. The substrate, the chemical substrate, the fuel, I'm going to use, I don't know, phi. And then we have for the fluid, they will have the probability density F. So the particles are described, they have a position, orientation in a given time. The substrate molecules have a position. They also have experience a reaction, so we characterize that or parameterize that with the reaction coordinate. And for the fluid, we have velocity and position. So essentially, it's going to be the same. I will write the conservation of the probability, the entropy of for each component. I will this will have related an entropy change of the particles, entropy change of the substrate, and an entropy change of the fluid, because since they have internal degrees of freedom and they are experiencing thermodynamic forces, we are going to have dissipation, irreversibilities. So I'm separating for the three components that we have in the system. Each component can be characterized with some variables. On general, the phase space is position of the whole system is position, orientation, reaction coordinate. And And yeah, so I will try to write everything for the particles, for the evolution of the particles. This case, we will have a velocity. This is the gradient in the Euclidean space of this density probability. Here we have the, so we will have some currents. That is the current in the Euclidean space, and then the gradient of the current in the orientational space. And then we can have more, but this is the main ones. Are we okay? Do you have questions? So this is because the particle not only depends on the position, also on the orientation. So I'm going to analyze the particle not only in the Euclidean space, but also in the orientational space. The entropy production, in this case, I will take advantage of what I already explained, is just the current, probability current, times these are vectors, times that product, the thermodynamic force, that is going to be the chemical potential of the particles. But not only that, because we have two currents. So we also have for the orientation and the orientation space. And this is the force. So this is the force to produce movement of the particles in the Euclidean space, and this is the force to produce movement of the particle in the rotational space. It means the rotation of the particle. And all this integrated in the whole phase space. So this is the, sorry, I started to write bigger here.
So in this picture, the interactions between the particles are encoded in J of X. Is that right?
Are sorry?
The particles repel or something. They have some sort of, they interact with each other. Is that encoded in the current in X?
Yeah, they will. Yes. So I'm here analyzing what's going on for one particle. So let's understand what's happening, or the dynamics of one particle, and then, of course, because we are going to talk about the probabilities, they are going to also consider not only the interaction among themselves, but also here we will obtain dependence on the concentration field and in the fluid field.
Okay.
These dependencies, maybe they are going to be a bit clearer. If I write the chemical potential for the particle, it's the entropic part is the KBT logarithm, the logarithm of the probability density, plus, so here it comes a term. No.
So chi is a delta function of x or something? It's something like x minus x0. X is the parameter that tells you where you're on the, yeah. So chi is a function of x, right?
Yes.
Is it a function like a delta function? Is it something like delta of x minus x0 or something like that? Or?
No, this is not necessarily a delta function, not necessarily. But
so the particle is spread out over the whole thing?
Oh, yeah, no. That is, in general, it's not necessarily a delta function, but then to interpret that the particle is indeed a point, it's a delta function, it's going to be this. Yeah, no, you are right. This is going to be approximately a delta function of the position of the particle, E. Yeah, but this is a sum. X is going to be the sum over E, that is the number of particles of this.
So it's all the particles?
All the particles, yes, because we have, I don't know, n particles, from 1 equal to 1 to n. This is going to be...
V is a function of x, or what is the V that appears there?
The function of, which is
you have
function
d chi dt equals V dot del schist of chi, the top equation.
Yeah, all this is a function of x.
V is a function of x?
No, this is an independent variable. This is the velocity of the fluid molecules. I'm going to use that because when we perform the cross graining, Yeah, we needed that to be independent. No, but this is independent. It can also be if we are not describing to that.
V is not a function of x.
No, here is not
Just
function.
a constant.
It's an independent variable of my system because it's the velocity, the fluid molecule's velocity. I'm separating.
But chi doesn't depend on v. I'm confused.
Okay, no, it's because I'm considering, if I'm describing the fluid molecules, I'm considering that they are described by a position and by a velocity. So in the macroscopic...
So chi depends on v.
Yeah, yeah, yes.
Well, then you need to put a v in the function of chi.
Yes, because if we see here...
So is there a v in the function of chi or not? Does chi depend on v? Is there another parameter in
Yeah,
chi that you forgot to
yeah,
write?
it's going to depend on v, but one condition is that when we integrate this on v,
Yes.
it's going to converge. It means that in v, chi should be something with a delta, or should be...
That's not what I asked. What I asked is chi a function of v? Is it just a function of x, n, and t, or is it also a function of v?
Strictly, yes.
I don't know what strictly means. It's either yes or no.
No, it's not going to depend. If we take the particle, if we only study the particle is characterized by a position and orientation, so it's not going to be a function of v. What is going to be a function of v is only the fluid distribution, for the probability distribution for the fluid. We can because I need later to do an integral. If we want to do a coarse graining, everything is going to be integrated in B. That's the reason. So
fine, but the first term doesn't depend on v. The first term, d chi dt, is independent of v.
Yeah.
But you're going to integrate it over v.
But you say that if here is v, it should also depend on b directly. It's what I misunderstanding you. Sorry.
That's what I would have thought. But you say it's not. It doesn't depend on v, so that's why I'm confused. But you can keep going. But I can admit that I'm confused.
No. Let's put it in this way. I can divide it in explicit variables. Chi depends explicitly on x and n.
Okay.
That's it.
Okay.
That's it. Okay. So I was building the chemical potential for the particles. It depends on the entropic part. And then this is other potential that is going to be the exclusion potential because the particle cannot overlap. So there is an interaction between the particles. And we also have another term that it's in the n space that we call it they call it the rotational potential, which allows us to explain why the particles can align with some fields, like with concentration fields or temperature fields. This is very important. And then the last term and perhaps the key term is the surface energy of the particle, because the particle has an interface between the particle and the fluid, and there is a physical interface with physical chemical properties that will give us a result, a surface energy that is going to depend on the surface tension. Okay, so far here we are considering the interaction between particles. Here we are considering the interaction of the particle and the fields to orientate because they can orientate with the field, and this is the term how the particle is also interacting with the concentration field, because this one is also going to depend on the concentration on the surface of the particle.
Sorry, phi of x is the concentration of the substrate, right?
Well,
is it a different phi?
Yeah, it's a different phi. Let's
Okay.
put phi sub p. Yeah. But this is for the interaction between particles. Interaction particle-particle. This is interaction particle with concentration gradients, and this is the interaction between the particle and the fields.
I'm also confused because you have this x vector. It's a vector in in 3n dimensional space,
Yes.
or it's a vector in three dimensions?
Three dimensions. Three.
Because but it has to depend on the position of all the other particles. No?
Yeah, I know. Usually in this approach we focus on one particle, so we are working with 3 dimensions. 3.
Okay.
But I get it. I get your point.
And then phi is what? It's
Phi,
some kind of mean field effect of the cloud of other particles on the particle?
Yep.
Okay.
Exactly. It can. It's really depend on the density. Of the probability density of the particles at a given position. That's going to be something like this.
And so it also depends, I guess, on the details of their interactions, right? So if you went from like a hard sphere to a soft sphere, phi would change somehow.
Absolutely, yes.
And you could calculate that? Is that something you can derive? Because you said you're going to go from microscopic to macro. This is already macroscopic, right?
Yeah. This is the reason thermodynamics kind of help us to summarize and to simplify a bunch of things. Keeping as the main message to be able to all this to have thermodynamic consistency. And yes, we are not going from these very, very microscopic details. This is completely true. I agree with you. So we just here, for instance, we just propose that this is going to depend on the probability density. And at the end, when we go to Langevin, it's going to become in potential, considering that they are hard spheres or more or less soft spheres, and so on. So, but all this is to be able to find the structure of the dynamical equations. Of course, for instance, when we are using on Sager, we have some coefficients. These are Sager coefficients, matrix of coefficients. There are some transport coefficients that should be found through theory, other theories, or from molecular simulations. So yeah, this is not. Yeah, I cannot say I'm not departing from atoms or molecules to build everything. No, yes, in some point. This is the reason it's mesoscopic. It's not microscopic at all.
It is confusing because you started describing these Janus particles and some number of them with positions, right? And then you immediately moved into this kind of mean field without really saying that you were doing that.
But the point is that the system is composed of n particles. And I'm going to, each particle can be described. Yeah, I'm sorry, maybe it was confusing because classically what we do is what you are saying in statistical, non-equilibrium statistical physics. But then we are going to focus on what's going on one particle at the level of one particle. And then we try also to understand what's going on at the level of the surface where the chemical reaction is taking place. This is the difference with the classical approaches. It's the way how we interpret the systems. So I agree. This is not very well known. It's not very used. But for me, it's a very nice and powerful tool because I apply. We can apply a recipe. The important thing is to define the independent variables, describing each component of the system, and then. That's going to be the hardest part. Other than that, it's going to be just some maths, and of course being able to understand energetically how my component, the energy of my component how varies because it should interact with other particles, it should interact with the other fields, and so on. So this is thermodynamics. Indeed, this is thermodynamics. I'm not starting from from molecule levels to build all in 3n dimensions. No. So I'm sorry if I wasn't clear at all at the beginning of my talk. This is another approach, another formalism. Other question, maybe I'm not going to be able to reach my goal. Something that for me is very important. Once we understand this, we can also define the chemical potential for the substrate and for the fluid molecules, and then we will write we use Onsager formalism, so we know that the current probability in the Euclidean space will depend on a matrix L of coefficients over T that accounts for the movement of the particles in X due to the thermodynamic force of the particles in X. That is going to be the gradient of, there is a dot product, the gradient of the chemical potential of the particles in X. But also the particles can move because of the substrate. And what I'm using here, the notation, and that is because the gradient of the chemical potential of the substrate is also affecting that. This is very well known as if we see this at the level of the diffusion, this is cross diffusion. This is the movement of a particle because of the gradients of other component. This is Maxwell Stefan also proposed that the cross diffusion. So it's a non-equilibrium process, very well understood since, I don't know, almost 100 years ago. And I can keep going because it's the movement of the particles because of the fluid, molecular fluid diffusion in X space. So we are going to have something like this. If I'm not forgetting another term, we can replace the chemical potential for the particle, and we can define this. So this is the hardest because or maybe it's not the hardest, because this matrix, it's just the identity times the diffusivity of the particles in the medium over Kb. If we consider that, we can write the first term of this current as dp over kbt. Here is a minus times k, and here, okay, I'm going fast. This plus this kbt is not here, is here, kbt, and the gradient of, because I'm using that definition, so we'll have here the exclusion potential, the rotational potential, and the surface energy. Of course, we are going to have more terms. I just want to mention here that this orientation potential only depends on n. So since I'm taking the gradient in x, this is going to be 0. This gradient here is what is going to give rise to the exclusion force. And this here, so this part is going to be the exclusion force. And this here is going to define the driving force, or as I call it, the phoretic force. We can also define here, if we define the chemical potential for the substrate, it essentially only depends on the entropic part. So it's going to be, I'm going fast here, the substrate times the gradient of the concentration of the concentration, not of the probability of the substrate. Yeah, just this one, because the other term that will come from the reaction only depends on alpha, and alpha doesn't depend on x. And then we can also have for the fluid and so on. But I just wanted to arrive at least to this part, because if we insert this into the Fokker-Planck, of course we also write this for the orientation space. But the important is that we replace this flux and this flux current into the Fokker-Planck equation for the particle, and we want to obtain the Langevin-like equations. We will see that this is going to be for the noise because of thermal noise, and this part is going to be, as I mentioned, for the exclusion force, and this one for the phoretic force. So we are going to have something like the evolution of the particle. It's going to be yeah, and I cannot forget that we have a fluid, so we will have the hydrodynamic force plus the exclusion force plus the phoretic force, and then we have the noise. That is going to be something general, or just the diffusivity of the particle times the white noise. This phoretic force is defined from I mentioned here that it's going to depend on the surface energy. So there is a formalism. This is another thermodynamic formalism where this phoretic force is going to be proportional to the surface gradient of the surface tension on the surface. And this variable, the surface tension, depends on concentration and temperature. So it means that the phoretic force will depend on the variation of the concentration in my system. If we also consider the variation of the temperatures in the system, they are going to be here, and that's the reason why we will hear in some fields about chemotaxis, diffusion phoresis, thermophoresis. It comes from here, from this phoretic term, and we can have it. Yeah, we can build it. Yeah, no, this is another paper, but this is a well definition from very well established. And finally, for the orientation, we are going to have something similar, that essentially we have a rotation matrix times the derivative of the gradient on n of the rotation potential. We could have another terms, but the most important here is this one, the orientation potential, and then we will have a noise for the rotation.
I'm a little confused because you said you're doing thermodynamics, but you just wrote down the equation for a single particle, right? I mean, for instance, the noise on the single particle, it's not just the diffusivity of the particle. The other particles are buffeting it, right? Other particles are hitting that particle, and that causes some of the jerks.
Yeah,
but also the fluid is hitting the particle.
Yeah, yes. No. Here, from the Fokker-Planck equation, we have one term with the velocity that when we integrate and then to obtain the Fokker-Planck equation is going to be the hydrodynamic force. Because we are building this is for the probability of the particles having a position and an orientation. When from the Fokker-Planck equation, we are going to obtain is the set. Yeah, because we have n particles, we are going to have the set. So this is, I forgot to say that this is for the particle I, for the particle I, for the particle I.
But it's okay.
Yeah. If
you actually wrote down like the physical dynamics of the particles, then the force on particle I would depend on the positions of all the other particles. But you don't have that, right? You have this. This is kind of a fake Langevin that happens to maybe reproduce the same distribution of positions, but like it's not what you would see in an experiment, no? Because the position of particle I plus 1, if it happens to overlap with particle I, it doesn't create a very large force in your picture.
No, but I let me disagree with that because this is a general potential that we are not very focused on defining this potential at this level, but we know when we go from Fokker-Planck for Langevin equations, that, for instance, is going to be the term of the exclusion force, and then we can define it.
Sorry, that term depends on the positions of all the other particles.
Yeah.
It depends on 3n dimensional quantities.
Yeah, it will depend on. This is for the particle E. Is going to depend on the particles that are in a given surrounding around it. We can define this potential to match the experiments.
But how did it come from the thing to the left, which does you said only depends on the position of one particle?
No, I get it. This is
from my perspective, I would start with the Langevin equation with the detailed interaction between the particles, and then I would derive the Fokker-Planck from that, right? But you've done this thing with Fokker-Planck, which is like in one particle coordinate, and now you're saying from that you're writing this Langevin that seems like just the microscopic description.
Yeah, but that's the different approach that we are using. I agree. It's more for people. It's more naturally to start from Langevin and then write Fokker-Planck. No, I agree. It's what I have seen. I have had some questions from my colleagues too, as you are doing here. We have the limitations. Yes. At the end, we will arrive to, there is a force, and then we just define the force here in Langevin. I agree. We could have a start in Langevin and then have more information to solve Fokker-Planck. Yeah, I agree. No, on that, I agree.
Sorry, the force doesn't come from something you just wrote here.
This force.
Yeah, it's not related to J of x, for instance.
No, it is because when we replace this current into the Langevin equation, and we integrate in the other variables in V and alpha, so on. We'll have the Fokker-Planck equation we'll have the Fokker-Planck equation for the particle in X and N and T that is going to depend on something that is the second derivative of chi plus something like this that is the gradient of the gradient of these other potentials that I was mentioning. So from here we can use Ethos or Stratonovich to arrive to like Langevin. Yeah, indeed, I forgot to say this is overdamped Langevin equations. Yeah, indeed, I forgot to say that. But since these are probabilities, of course, for this coordinate, this comes from the independent coordinate. It's not going to be. It's only one coordinate. But then, since this is a probability, of course, we have to describe this for n particles. So this is the equation for the n particle of my system. This is we are going. In the opposite direction to obtain the evolution equations. This is mainly because when we also solve or find the Fokker-Planck equations for the chemical fuel, we can do the cross graining to obtain the concentration field. So we are going to be able to have a multi-scale model for the discrete particles or entities, and then for the continuum that is going to be for the concentration field and also hydrodynamics field.
So when I think of Janus particles, I think of like the most classic thing they do is they separate. They phase separate, right? The motility-induced phase separation.
Yes.
So is that something that can be described in this picture when you have very high correlations between the positions of the particles and they overlap and they displace the fluid around them?
Yes.
Okay.
No, yes, because all this is going to be coupled. All this, for instance, this, as I was mentioning, is going to depend on the concentration, even temperature. This is going to depend on the fluid velocity. This one depends on the position. This concentration and temperature also depends on the position, because we are going to have the equation for the concentration in my system. That is going to be something like this, plus a very important term that is the reaction, that is the sum over I from equal to 1 to n of in the position of the particle, because the reaction only takes place at the position of the particle, times the reaction rate. The reaction rate at a particle, at a given particle, that this is defined just like the concentration time, the kinetic constant times the concentration. This is a first approach.
Your particles you're treating point-like.
Yeah.
Okay, but you wouldn't have MIPS then, right? Because they can't. MIPS relies on them contacting.
Yeah, but then that depends on how you define this potential.
Sure. Okay.
Yeah. And one important mechanism is that when the particle reacts here is consuming, the concentration of the substrate decrease here, but the concentration of the product increase here, and we will have a movement, let's say, in this direction.
Yeah,
but then the other particle also creates something here, so this one is going to,
but this is the effect that you would want to describe a dilute system. But if another particle is literally touching the second particle from behind, it displaces the fluid and the substrate.
Yes.
Is that captured here? The displacement of you have a particle literally behind another. They're touching each other.
Yeah. Because we must be aware that we consider also the hydrodynamics of the system. We have to solve the hydrodynamic equation, and then is where we have this is the normal tensor and the viscous tensor, and we have here the active tensor. This active tensor is going to depend also in the surface energy tension, surface tension, yeah. So this tensor, this is kind of, you can see as the source of momentum, or we can, from defining the Fokker-Planck equation for the fluid molecules and considering the coupling processes from Onsager formalism, we can arrive to this term that is going to account of, okay, the particle is moving, is going to displace the fluid. The fluid is also going to exert a force in the particle. If they are very close, this one is going to take a main role, the exclusion force, but the one that is driving everything is the phoretic force. They are not going to move only because of the interactions with the fluid, or because they are crashing with another particles in some cases, but also because there is a actual thermodynamic force coming from the surface tension that is kind of a marangoni, but at the level of the particle surface. So this is the whole picture. We have, and there is a coupling and all the equations. This depends on the position, concentration. This depends on all the variables. This is going to depend on the position of the particle. So all the dynamics are coupled. And one of the conclusions, for instance, in the community of active particles, usually is assumed the concentration field more or less constant, and the active velocity or the active force constant, but I'm saying not. It also depends on the medium, and you are perturbing the medium. So it's what you are saying. There is a constant coupling because particle moves the fluid interacts with the particle, and then I am also saying that the concentration fields affect Professor Nathan.
I just want to know if there are other questions. Does anybody else have any other question? No? Okay, so of course you guys can continue, but maybe we'll just thank you. Okay, so thanks very much.
No, you're welcome. Thank you. I just wanted to comment that with the active particles, I'm also working on extending this approach to be able to describe the movement of cells and to finally describe self-sorting. That is also kind of this phase separation, because they have non-reciprocal interactions when they interact from cell A and cell B. So that was my final comment, and this is kind of the big project that I want to work. And these criteria for the structure formation, that is my main goal, to generalize that. Thank you very much for your attention and for the invitation, Professor Nathan, and yeah. Thank you. I'm sorry? Friday.